Hi, my name is Peter Røen, and in this video I will show you how you can use my web server, which you find at this highlighted web page, Stop Model Hindrance, that has a focus on detecting steric and topological obstructions for aligning models of proteins onto the correct 3D structure. Can also be used for normal structure comparison, but it's really focused on comparing models to the correct 3D structure of proteins. There are currently two versions. There's the intended version 1.0, but there are some technical issues with the graphics and from MATLAB servers, so it's not that stable, and I made a simpler version 0.5 that's clearly more stable, and that's the one I'll focus on. I have opened it in this window. So in order to have some data to work on, you need to upload PDB files. They usually have the last name .pdb. It's not needed. In CASP, usually the target files do not have the ending .pdb, so it accepts any ending, but it needs to be a protein database file type. You can press select a file, but since the browser doesn't know anything about your filing system, you might be many clicks away from finding the file you want. So instead, it's easier to simply drag and drop a file here. So this is target 1046 from the CASP 14 event. That was the target, and I just right now only pick one model of this file from the same event, and it's loaded here. So let's just make a figure here. I only have one model, so I can only choose this one protein to make a model from comparison to the target. So there's an alignment and structural overlay of the two structure things finding place first, and since it's focused on protein models, it starts out by searching for an exact sequence match from the entire target file as a subset of the model. Usually the models have a bigger sequence than the native structure. So there are other options. You could make a general sequence based alignment, and then that's supplied up to with RMSD superposition afterwards. And finally you can make a global RMSD where the shortest of the two structures is forced to be aligned to a subset of the other. The entire shorter structure is aligned to a subset of the bigger one, with allowing one gap of at most 10 residues. It's simply needed. We need a global way of superimposing the structures to talk about the topology. So the output here states it found one self-intersection in the morph from the one structure to the other structure. It's what it's called an essential one. I'll talk about that. You get an RMSD. You get a number here saying how many angstrom on average of steric clashing is taking place during the linear interpolation from the one structure to the other structure. So, and you can see this highlighted in the figure. The black dots, spots here are where these residue pairs get into too short a distance while morphing from the one structure to the other. And the red E says that there's a self-intersection between these residues. So residue about, you can see it here, 22 and 39. Actually here the backbone passes through itself when going from the one structure to the other structure. It's sometimes difficult to see what's going on when you're looking at the alpha carbon trace. So a possibility is to click here, backbone smoothing, and redo the it's a new alignment of the smoothed backbones, and usually it's easier visually to see what's going on here. See if I can yeah, so from this angle you can see in front here part of the chain in the target, the correct structure is going, well, this way around, but in the blue, the model, it's going the opposite way around. So what's going on here is basically like you're going from a left-handed loop to a right-handed loop, and if you try to do that following the normal structural alignment, the backbone is actually passing through itself here. Of course, I cannot do that with my wire, but the program actually checks if it's possible to take a detour inside the configuration space to avoid this self-intersection. But right now, the program is only allowed to look for a detour involving 15 amino acids. And this loop is slightly longer, I think it's 17 or something like that. So if I just say plug in, you're allowed to use 25 amino acids, then it can tell that it can avoid that self-intersection. And what the program actually checks is that if at the time in the morph between the two structures where there's a self-intersection, then it checks if a surface spanned by the loop is disjoint from the rest of the curve. Because if it is that, then you can do that trick, getting from the one side to the other side. But if there's another part of the protein structure sticking through that loop, then it's not possible, or you would make new self-intersections if you actually try to avoid the self-intersection in closing the loop. So this is the check going on. So it's the user, you as a user need to define how many residues the program is allowed to rearrange during the morph to see if it's a self-intersection that's severe for your purpose or not. If you work with protein structure refinement, my guess is you would find all sorts of such self-intersections severe, because in the presence of such a self-intersection, you can actually not improve the structure by going in the direction of minimizing RMSD or getting a bigger global distance test score, because going in that direction is going to cause the self-intersection, first steric problems and then self-intersection of the curve of the protein. So this motion that's needed here actually says that you have to go a detour to get to the correct fold, and that means that this model is actually in, you could say, in RMSD space, not in a basin of abstraction of the native structure. You need to go to larger RMSDs in order to get them lower, at least when you have to go through self-avoiding structures. So that's an example where we have just one model. Let me upload here another CASP target. And together with that, a bunch of models, and I also include the other target. So I now drop 12 PDB files here. It takes a little while for reading them. It's done now, and we have them. So now I can decide which of these models I want to make figures for, or I can start by saying I want to compare the target versus all models but not producing figures. That's done now, and as we use an exact sequence match between the protein structures, we of course cannot get a sequence match to the completely different protein, the other target we used before. So in that case you do not get a comparison. If you switch to just using RMST, of course you do get a comparison. So in this table you can let's just switch back to using the normal alpha carbon and perhaps also use global RMST. The RMST search is a little bit slower because it needs to go through a lot more possibilities. Yeah, so we can sort this after the column you like, and we see here that there are here more and more overlap taking place between model. We could perhaps look at number 15.1 here. So there are no self-intersections in the structure, but there are two places where you get sort of intersteric problems when trying to morph from the one structure to the other structure. So that's what you see here. And if we go to this one, number 15.5, here it is. Let's switch back to the exact sequence match. It's more natural in this when it's a model of that concrete protein. So in this case we have 4 self-intersections when using the alpha carbon backbone trace. One of them is called to be essential. You see it here. It's between a residue a little bit before 50 and up to here you can recognize 102. So you need to rearrange a big part of the protein if you want to unravel that self-intersection. To better see what's going on, I perhaps switch to apply the smoothing of the backbone, and what you can see here is that the 2 yellow parts of the curve here, that's how it is in nature in the target. You have this part in front, that part behind us, but in the model this part of the model actually enters into the loop of the other one. So instead of having the 2 loops away from each other, one of them is passing through the other one. So that's the type of self-intersection that happened here. It's not an uncommon mistake, because you could say the distance matrices is not that different between the target and the model. It's just sort of a threading going the wrong way around itself at this point. You can actually force and say, if you're allowed to rearrange large parts of the structure, then it will actually say, well, I can remove that one, and it then finds that along the detour in the configuration space actually you can get from the one structure into the other structure through a self-avoiding morph. And you see here that one of these omega moves, or itemized moves as they're called in knot theory, involves almost 54 residues or line segments, the length of that one. If we do the same calculation using the alpha carbon backbone, it is again able to see that it finds a morph from between the two structures through self-avoiding configurations. But now it gets the self-avoiding morph in a different way. It uses a Rademaster move of type 2, or making a move of type 2, that only involves 33 amino acids. And what it's doing is actually it can sometimes find pairings of 2 self-intersections that it can unravel at once. And what's going on there is basically that if you have like where's the camera? A loop here in the structure, and that passes through another part of the curve at some point during the morph, then it can check that these 2 self-intersections, again, if there's nothing in between here in that loop it defined, then it can contract this part and make it go on the other side. So it's like making an undercrossing to an overcrossing here. So that's another possibility of finding a self-avoiding path between the 2 structures that you see here. So these are the main functionalities when considering judging if your models have the correct topology while knowing the correct answer, namely knowing the target. You can also do an all against all structural comparison, and you do that on this list of models, and since my list of models is a little bit long now, I'll just take fewer models to my list here, and for this comparison we need to switch to that it's geometric, because the sequences are not the same necessarily of the models, so the sequence comparison for the alignment doesn't work. So here I can do all against all structural comparison, and it's based on RMSD, and again, one of the, you can move this to see the names. And an interesting finding, for instance, 15 is a lot here. So if we go down, it's saying that we are not allowed to rearrange a third of the protein, but only 15 amino acids at a time. Sorry, hit the wrong button here. Then you will see that quite often between the models of the same target here, actually from the same group, there are many self-intersections, and some of them are essential. So you can use this to judge if your set of models actually share threading or topology, depending on the word you like to use, or if you have a list of homologous structures that you are using for your model prediction, then you can check if they are actually threaded in the same way, or there might be sometimes actually, you can see in the paper, it's not that uncommon that proteins that are share homology class do not share threading. So that might be an issue you want to take a look at. That's the main ways of using the server. Please don't press save the figure for the time being. This makes the browser go down. Here's the link to the YouTube video coming up. In the intended version that I have here, it's basically the same setup, and I can just shortly show you. If I put in a target here and a model and generate figures, the main difference here, yes, is that for not all self-intersections, but at least a representative set of them up to the first 4 of them, there's room for, you get a zoom of that part of the protein such that it's easier to see what's going on. But luckily this graphic setup is not that stable. You can use it, sometimes it works, sometimes it doesn't, and good people using time on trying to come up with a fix. So hopefully it works pretty soon. That's it. Hope this can be helpful in your structure prediction or in your study of a family of protein structures.